A couple of things. I want to show you all this. I've not taken dip and snuff, but in one of the videos I mentioned O'Keeffe's working hands. My hands are already starting to dry out for the winter. This is what that is, and I don't get money from O'Keeffe, so I'm just telling you this is good stuff. So it comes in a tube, but unfortunately the tube's about that big, so it's probably not good to carry around clinicals. But this is the only thing that keeps my hands from splitting. So that's number one. Number two, there. Oh, okay. It is smaller tube. Good. I've only seen these great big tubes. All right, so they're for a while. This is all you could get. This thing was all you could get. It's what, $3.99?
For only $3.99.
For only $3.99. But wait.
Yeah.
But wait, there's more.
There's more. If you act now, for a separate processing and handling fee. So I don't think I got it posted, but I did kind of like a voiceover for the positioning for Monday for the second hour, I think it was. I'll get that posted up today. This will probably hit tomorrow because I've still got to edit the other one. All right, so when I'm trying to do something for my office, in a lot of cases, it's just weird. It's just weird. You're in your office alone, you're looking at something, you're talking, and I stop and start, and I stop and start because I get stuck on something, and then I'll restart it. And by the time I finally get it done, I'm so pissed that, that I might have said something along in a recording. So I don't think that there is anything, but if ever I record something, in front of an empty room or from my office, and I missed something I should not have said on a recording, just go, Okay, so anyway, it's really aggravating. So I left my book and I left my notes. I brought some other stuff I want to show you. So again, kind of flying by the seat of my pants, trying to remember what I had in my notes and making sure that I covered it all. So I am going to have to borrow a book, but not just right away. So what we're going to talk about today is electromagnetism and how it is that we take electricity and we create magnetism, and how we take magnetism and we create electricity. So until, I don't know, 19th century, they were thought of as two separate entities, electricity and magnetism, and it wasn't until then that it was discovered that they're actually one and the same. So it's one of the fundamental forces. We have four fundamental forces, and that would be gravity, obviously. Gravity, you can't really do anything about gravity. So gravity, and then there's the nuclear forces. On the atomic level, there's a strong and weak nuclear force, and then the other is electromagnetism. So it's one of the four fundamental forces. How that plays into this, it doesn't, but it's just FYI. So the start of the understanding of that, they're kind of one and the same, is that it was Galvani was, when y'all were going through AMP, did they show you the frog video where they touched, electrodes and severed frog leg would jump? No, but it's a thing, and it was first identified or attributed that it was identified by Luigi Galvani. So he was in his lab, and some things kind of came together as they often do in the lab. Discovery of X-rays was the same way. Certain things were in place that were kind of accidental, and then a discovery was made, right? And so some electrodes touched this frog leg, and the frog leg twitched. It was a severed frog leg. And we understand that nerves work off of electricity, and that's why, like I was talking about on Wednesday, the stimulator that they put on the side of the patient's head, they energize that stimulator, and the patient kind of twitches, and that's because it's firing the nerves, and the nerves are causing the muscles to twitch. And the same thing that happened with frog. So in the late 19th century, they were doing a lot of research. When Röntgen discovered X-rays, he wasn't out looking for x-rays. Everybody was just trying to figure out what electricity is. And that's all he was doing, was playing with electricity and trying to describe all the ways that it behaves. So the problem with understanding electricity was having a consistent source of electromotive force, voltage, push and amperage, electricity. And so a guy named Alessandro Volta is accredited with making the first battery. Y'all don't know this particular joy, but you know, used to, whenever they put fillings in your mouth, the fillings were made of metal. Okay, I don't know what the metal was, but it was metal. If you ask an old person to open their mouth, then what you'll see is, you know, obviously the molars, and then if they had a cavity, unless it's been replaced, it's going to be filled in with this metallic stuff. Also, the most popular gums at the time, chewing gums, were, let's see, Wrigley's Spearmint, Double Mint, Peppermint. You know, those three were and Juicy Fruit were, you know, the big ones. I don't know if they still are or not. I don't chew gum, but they had a aluminum foil wrapper around each stick of gum. And sometimes you know, as a kid, you just peel that thing off and you pop the gum in your mouth, you start chewing away, and not all of that aluminum foil would come off, and you bite down on it, and what you had is this filling in your mouth, and then you had that aluminum foil, and they come together, and you would come unglued. And what it was dissimilar metals coming together to create an electric current in your tooth, and it hurt, right? So that was the basis for Volta's, what they refer to as a electric pile. And what it was dissimilar metals stuck together to create a source of electromotive force, this battery. And I keep saying attributed to. There is some evidence and some hypotheses and theories that they created batteries out of pastes like 2,000 years ago. So whether or not you know, he actually made the first battery, I don't know, but that's what we're going with for now, because everything else is anecdotal. So if you hear something about, oh well, you know, they had batteries back in ancient Egypt, okay, well maybe they did, maybe they didn't. We don't have definitive proof of that. We do know that Volta created one that was, you know, sustainable. So so now we have a force or a source of electricity, and experimentation takes place. And a guy named Ørsted, a Danish guy, and see, I don't even have my own markers down here. See if I have any decent markers. Okay, we can get through this. So Ørsted, he's in his lab, and they say it's Ørsted's experiment. Maybe he was experimenting with certain things, but I again think that the elements were just in the right place at the right time, and he happened to make a discovery. So he was experimenting with stuff. Whether or not he was experimenting expecting that something like this was going to happen, I can't tell you. But what he had were the elements that he had in place was that he had an electric circuit. All right, so with an electric circuit, for electricity, you have to have a source of electromotive force, right? You have to have something that's going to push voltage, which will push amperage through a circuit. So he had a battery. And anytime you see a symbol that looks like kind of like that, that's representative of the voltaic pile. You know, dissimilar things stacked together to create a battery. So he had a battery plugged into this thing, and he also had a switch. So a switch kind of looks like an open door if you've ever seen a partially open door, if you've ever seen a diagram, you know, schematic of a house. Kind of looks like that. So when we have an open switch, what that means is the switch is off, it's not making contact. So you remember the ways that we can electrify. You got rubbing or friction, and you've got induction, and then you've got, the third one was? Or induction, yeah. But the third one that's not induction or friction was? Contact, right. So you got contact, or did you say touching? So somebody said, I thought they said induction, could have been touching, but contact is touching. So when the switch is closed, what that means is electricity can flow. So he had all these things in place, but he also had a compass. And where the compass was, again, I can't really tell you. I'm going to stick it over here. And where does the compass generally point? North, right. So let's say north is that way. So we got north here. So switch is open, and compass is pointing towards the polar north. And he closes the switch, and electricity can flow. And when he does, he observes that the compass no longer points north, but it points at the wire. So what he did from this point, I don't know. Again, it's kind of lost to history, or just maybe it's not lost to history. Maybe he took this thing and he moved it all around, and consistently it pointed at the wire. So he has proven that once we get electricity, electricity involves the movement of charged particles. Any charged particle in motion creates magnetic field. Okay, so that's Ørsted's experiment. He proved that you can take electricity and create magnetism. So further exploration, and who came up with all this, I'm not 100% sure, but walking back through the laws of magnetism, how do we increase magnetism? What's Coulomb's law applied to magnetism? The first part of it is
The more you have, the more you
the more you have, the more you have. Right. So in this case, we've basically got one magnet. But if we took this wire, instead of having it just as a flat wire, if we took it and we coiled it up like that, so if we have the flat wire, let's go back to the flat wire for just a second. We go back to the flat wire. We can predict, the direction of the magnetic field. And you don't have to know this for the test. This has come off the registry, so this is just FYI in case you see it in another book or in another reference. The right-hand rule says that if you were to grab a wire and point your thumb in the direction of electron flow, then the magnetic field that sets up around that wire would be represented by your fingers. Okay? So now apply that over here. If I grab this, and let's say my electron flow is coming up the wire and going out that way, then my magnetic field's going around the wire like that. You follow me? So by putting, and I wish I brought my magnets, if I took the north end of a magnet and the south end of a magnet and I put them together, what would I have? A bigger magnet, right. So if the magnetic field's going around the wire like that, and it's going around the next wire like that, then those magnetic fields can overlap and join together, and I've got more magnetism. The more you have, the more you have, right? So what I've got in coiling that wire up is the ability to create a much larger, much stronger magnetic field, okay? So we can make some ridiculous magnetism by coiling wire up. You ever seen a video where a car's in a junkyard and they take this thing off of like a excavator and they just stick it to the top of a car and they can pick the car up? All that is electromagnet. So what it is inside that big flat thing, what they've got is coiled wire inside of it, okay? That coiled wire, they run electricity through it. They run electricity through it. It becomes strongly magnetized, and you can pick a car up with that thing. So how do you get rid of the car? Well, this is a temporary magnet. The defining characteristic of a temporary magnet is that you can shut it off, right? So they flip the switch, car drops into the crusher, and it crushes the car. So this is, in this orientation, what we're going to call this is a solenoid. Not really electromagnet, but a solenoid. And we'll get to electromagnet here in a minute. They're really pretty much the same thing, but Bushong makes that distinction, so I'm going to trust that that's the way it's going to come at you on the registry, so that's the way we're going to talk about it. A coil of wire with electricity running through it without any kind of metal core, we're just going to call a solenoid. So we use solenoids all over the place, and you just don't even know it. The common places that you use solenoid. is in your x-ray tube and your x-ray table. You know, you step on the button on the floor, and what do you hear? In a lot of cases, you hear kind of a clacking sound, right? It goes pop. And then you can move the table around, right? You reach up and you hit the buttons on the x-ray tube. What do you hear? Same thing, right? So what you've got in that, you can move the tube around. What you've got in that, let's say these are the rails on the ceiling. And then you've got, you know, the overhead crane system. And then you've got, you know, the x-ray tube is down here somewhere, right? So x-ray tube is somewhere down here. So you hit those buttons, and let's say you want to move the entire assembly, and what's happening is the reason it doesn't move well is because you've got, you know, maybe really strong springs pushing brakes up into this thing. And it just won't move. You know, you can tug on it, or highly recommend you don't do that. You know, rough handling is one of the second most common cause for tube failure. But you can't overpower these brakes, right? But you hit those buttons, and what you do is you activate a solenoid that pulls those locks away from it, and you can move it anywhere you want to go. Okay, so it's a solenoid. Same thing with the table. You know, you step on the button, and you activate those solenoids. You loose the brakes, and you can float the tabletop anywhere you want to go with it. You can make really, really strong magnets just with a coil of wire. In the hospitals, the doors that always stay open, you know, as I'm talking about, there's like you get to a wing of the hospital and there's doors that are always open, almost always open. Watch what happens when a fire alarm goes off. You know, automatically built into the safety system in the hospital, fire alarm goes off and those doors automatically close. Why is that? It's because there's solenoid in those brakes, or in those doors, in those locks that hold them open. And whenever a fire alarm goes off, that solenoid automatically deactivates, so the doors automatically close all by themselves. Okay, so you see them. You don't see them, but you see evidence of them all over the place, all over the hospital, and the equipment we use is solenoid. Solenoid, coil of wire with electric flow going through it. So one way that we can make it more efficient, before I draw this in there, one way we can make it more efficient is to concentrate those magnetic fields, okay? So what you might read in Bushong and other sources is that the transformers and the magnetism that we create with electricity is very, very, very efficient. And it is, but it's not perfectly efficient for a lot of different reasons. One is the resistance inherent in the wires themselves, right? So we've got electrons that go through the wires, and we always create two things anytime we have a current. One is heat, and the other is we've got a charged particle in motion, so we create magnetism. Exactly, so we create both of those things. That heat creates resistance, which creates heat, which creates resistance, and so on. So it's not 100% efficient. We lose some of our power to that resistance. Another thing is that not all of those magnetic fields completely overlap. Okay, so we do have inside of those wires overlapping magnetic fields that strengthen the magnetic field, but not all of that goes into that, you know, joint magnetic field. What we have around the wire are minimal magnetic fields that we refer to as eddy currents. So back to water. What is an eddy? You ever stood on the bank of a creek and you look down and the water's flowing, right? But it hits something, the water hits something, and what does it do? Okay, it might go backwards, or it might continue to go in the right direction, but it kind of spins, right? It just kind of spins. That's an eddy current, okay? So we have eddy currents around each one of those wires. So when we were talking about magnetism, what happened whenever we took a magnet? What happened to the magnetic field when we took a magnet and we put a piece of ferromagnetic material next to it? I have a word for it. I already mentioned it this morning. We induce magnetic field in the ferromagnetic material. So what if we take this coil of wire and we stick a ferromagnetic piece of material inside of the center of that coil of wire? We wrap the ferromagnetic material with our coil of wire. What would happen to those? What do you think might happen to those eddy currents? It just intensified, and they join the crowd, and now we've got a very much stronger magnet. Okay, so on the test, the fundamental difference between a electromagnet and a solenoid is that the electromagnet has a ferromagnetic core. Okay, otherwise they're identical, really. Okay, and again, I would, I'm a simple man. If I'm making a magnet with electricity through a coil of wire, whether or not it has a ferromagnetic core, it's electromagnet to me, right? But we're going to make that distinction. If it doesn't have a ferromagnetic core, it is a solenoid. If it does, then it's a electromagnet, okay? All right, so electromagnets and solenoids. All right, so, and that's Ørsted. Michael Faraday came along, and he said to himself, Self, if I can take electricity and make magnetism, can I take magnetism and make electricity? And as it turns out, yes, you can, okay? So, now I need you to turn and look at Faraday's law. Faraday's law is on page 86. So, here, I don't have to lean over you. All right, so Faraday's law has 4 parts to it, okay? So the strength of, the magnet, I'm good. The magnitude, thank you, Doug. The magnitude of the induced current depends on 4 factors, and that is the strength of the magnetic field. All right, so we've got a magnet. And a magnet creates, a magnetic field. Here we are back to, looks like mud. All right, so north and south. If we have a coil of wire over here, we can create a magnetic field, or we have a magnetic field, we can create a current in this coil of wire. And the strength of how much electricity we're going to create is dependent on, number one, the strength of the magnet. So if I have a little bitty magnet over here, am I going to create electricity in that coil of wire? Maybe. If I get it close enough, yeah, maybe. It's going to, but if I get this great big strong magnet, what can I create more of? More electricity. More electricity, right? So I've got magnetism. Now I'm creating electricity with the magnetism. Ørsted, we can create magnetism with electricity. Michael Faraday, now we're going to create electricity with magnetism. So the stronger the magnet, the more electricity we can create. That's number 1. Okay? So number 2, what does number 2 say? It says the velocity of the magnetic field as it moves past the conductor. So one thing that I did miss before I went on with this is that you can only create electricity with magnetism if the magnet is changing, if the magnetic field is changing. Okay? So let's get rid of my magnet and my magnetic field here, and let's say I've got, let's say I've got a magnet. Oddly enough, this eraser is magnetic. I've got a magnet, and I put it right there. Now I took it from over here. Where's the magnetic field in this magnet way over here? it's coming all around. Is there magnetic field interacting with that coil of wire? No minimum unit of magnetism, so yes. As I move closer to it, how much magnetism is this coil of wire receiving? In a word, more. The closer I get, the more it gets, right? So I move it in, and what I get is a flow of electrons. I'll make electrons blue. We get a flow of electrons that gets stronger and stronger and stronger the closer I get, and then I bring it to a stop. What did I have to have in order to make electricity in that wire with the magnet? Changing magnetic field. So if this is a permanent magnet, is the magnetic field changing at that point? No. The answer is no. So my flow goes away. Okay? If I pick it up and I pull it back again over this way, what do I get? Changing magnetic field. It was increasing as I went in, it's decreasing as I come back out. In both cases, the magnetic field is changing in relationship to the wire, and so I'm getting electricity. Okay, so now back to the second rule. You know, if I bring it in and I leave it there for a minute, and I pick it up and I pull it away, how much electricity do I get out of that? And we'll give it an arbitrary number and just call it 1. 1 whatever. You pick out your, you know, whatever unit you want to call it. We got 1. All right. Now I bring it back in, I stick it there, and I leave it for 30 seconds, and I take it away. Then I bring it back in 30 seconds later, it's still 1 minute. How much do I have now? Double. 2, right? So I got 2. Now we do it every 15 seconds, and what do I get? In a word? More, right. So the faster I move this in and out, the more electricity I have, right? Now I can move it this way, I can move it this way, right? Or I could put this thing on a power drill, and we know that electricity goes in the north end and out the south end, right? Or the magnetism goes in the north end and out the south. I think I just did that backwards. Anyway, it goes in one end and out the other, right? So we've got our orientation, let's say in this case, going this way. If I flip it around that way, what's our orientation of the magnetic field now?
Reverse.
It's exactly the opposite. Did our magnetic field change?
Yes.
Yeah, it did. It did. So if I put it on a power drill and I spun the power drill, what would happen to our magnetic field?
It would be changing constantly.
Be changing constantly, all the time, right? So if I did that, what would happen to our flow of electricity?
It would increase.
We'd have a lot, right?
Could you then use that electricity to power the drill that's turning it?
Yeah, you could. Yeah, and because of, yes, but because of it wouldn't. You're kind of thinking perpetual motion, right?
Yeah.
Yeah. Okay. So yes, you could, as long as it was going into a battery. But you're going to have loss. You know, you got mechanical energy expended, and then you've
You
got.
can't just infinitely
Yeah.
use it, but
Yeah.
you could use it.
Yeah.
In a way.
Theoretically,
Yeah.
you could. Yeah. 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 We haven't figured out perpetual motion yet, but that would get you longer life.
Yeah.
Right. So, number 1, how strong is the magnetic field? Number 2, how fast do you move the magnetic field in relationship to the coil of wire? In this case, it's flat wire. All right, so the angle of the conductor to the magnetic field, I don't really have a good visual for that, so just file that away. But the last one is the number of turns on the conductor. Okay, so how did we make a strong magnetic field? How did we make a solenoid and an electromagnet?
Ferromagnet in the middle.
Yeah, so we take and we coil the wire up. Now we've got overlapping magnetic fields. And if we do any one of these things, but especially spinning that thing around and around, we're going to create a ridiculous amount of electricity. Okay? So that's Faraday's law, essentially. So now let's apply both Faraday and Ørsted together, Ørsted said that you could take electricity, make a magnetic field. Faraday said, yeah, but you can also take a magnetic field and make electricity. So let's say I've got a coil of wire here, and I feed it a current. I flip a switch on, I create a current. Then what am I going to set up in this? When I've got a charged particle in motion, I create heat, but also create magnetic field, right? So I've got it coiled up, so I'm going to create a strong magnetic field, right? So if I move this other coil over next to it, I've got a magnetic field here. What am I going to get over here? Two things. Magnetic field, because
Induction.
we got electromagnetic induction, but because we created what over here? This is electromagnetic induction.
Electrical current.
Electrical current.
One over there.
And the electrical current creates your magnetic field, right? So, what though is missing in this? So I flipped the switch, I got electrons going that way. Hmm?
A battery.
Well, we got a battery. Let's just assume we got a battery over here. So everything's plugged into the battery, and we got a switch, close the switch, and electrons flow, right? But there's something missing.
The rheostat? Or is that included?
Well, we're gonna get there.
Alternating current.
Bingo. Okay, so why is alternating current important?
Because it changes the magnetic field.
Perfect. Changes the magnetic field. If I have electron flow through the wire, I'm going to create a magnetic field, but it's going to be a magnetic field that does not change. It's going to be constant. Yeah, what we have to have is not from a battery, but we have to be coming from a generator. Okay, so we've got alternating current, we've got direct current. Direct current, you see all the time. You use it all the time. You use both all the time. But your devices, your phone, what powers your phone and your tablet and your computer? Battery. So battery is a source of electromagnetic or electromotive force. So it's a source of electricity, but it's direct current. Okay, the current goes in one direction until your battery runs dead, or until you plug it in. Once you plug it into the wall, the electricity at the wall is alternating current. Alternating current goes in two directions, so that when it's going in one direction, I want to say the north chases the movement of the electrons. So let's go with that, and it doesn't matter if I'm wrong. You can come up to me after class and say you were wrong, and I say, okay, great. But I want to say north chases the movement of the electrons. So we've got north pole set up here. So our electron, or our magnetic field is, going in one direction. Let's say that way, yeah, that way. And then when it goes out that direction, that means it's coming back in this direction. So where's our north pole now? If it was down here with the electrons going that way, our north pole is going to be here. So this is then like you put your magnet on the drill and you're moving it around and around and around. So do I have a changing magnetic field? Answer is yes, I do. So if I've got a changing magnetic field here, then I can induce a consistent current there. Okay? This is electromagnetic induction. This is electricity creating magnetism to create electricity, which comes with magnetism. The magnetism over here doesn't really matter, but you have it, right? Okay? Bless you. Everybody with me? Ish. Okay, so what did I just draw? I've been drawing this all semester. It's part of the circuit. Specifically, what part of the circuit is this? That's not the rheostat. This got two coils. Step up and step down transformer. All right, so that's where we're going next, is step up and step down transformer. All right, I'm gonna draw the whole thing out again. So what's the first thing the electricity gets to? Sort of. Y'all know this. It comes into the hospital and it goes to, first thing is the
Transformer, auto transformer.
auto transformer, which is a
Single coil.
single coil. And it's got a core in it as well. I'm not gonna draw that, but it's a single coil of wire, and we call it a, you said it, rheostat. It's a rheostat. Why is it a rheostat?
Because you can control it.
Because you can turn it up and turn it down, right? So if I spread the contacts, if I have set contacts on the primary side, and I change the contacts, let's don't even do that. I put the contacts on the secondary side in exactly the same spot, then I have no change in the voltage or amperage as it comes, you know, as well, let me back up. So if I supply this with alternating current, what do I set up?
Alternating current.
Oh, I got alternating
Electromagnetic
current.
field.
Yeah, it's a magnetic field, it's a changing magnetic field, right? Because I've got alternating current, I've got a changing magnetic field that goes back and forth and back and forth. Okay, so if I plug into the secondary side in exactly the same spot, then I do no real work, right? So if you flip over to the transformer laws, all right, so we're on page 88. Transformer law, there's two different transformer laws. One as it applies to voltage and one as it applies to amperage. So the top one on page 88 applies to voltage. So voltage on the secondary side over voltage on the primary side, and notice, is equal to N means the number of turns on the secondary side over primary side. So voltage secondary, voltage primary, voltage secondary over voltage primary is equal to numbers secondary over numbers primary. Okay, so what's our relationship there?
Direct.
It's a direct relationship, right? The only thing that would change is this portion of the equation, right? So let's simplify this, all right? So if I have voltage, if I supply this thing with 1 volt, and I want to see how much voltage I supply this thing with 1 volt. I want to see how much voltage I'm going to have after running it through these coils of wire. I don't know how much voltage I've got now, so it's X is equal to, in our illustration over here, what's the ratio of turns I had on the primary side to the secondary side? They're identical, right? So equals 1 over 1. Okay, so how do I solve that?
That's direct. Yeah.
Cross multiply, right? So I have 1x is equal to 1, divide both sides by 1, and what I have, x is equal to 1. So what did I do here?
No.
Not one thing,
Yeah.
right? I didn't do anything. But let's say that I take my contacts on the secondary side and I spread them out so that I've got twice as many on the
Secondary.
as I have on the
Primary.
All right, so let's rework this and see what happens. So I've got more turns now on the
Secondary.
than I had on the
Primary.
primary side. Still don't know what my voltage is going to be. But my voltage on the primary side is still 1. Number of turns on the secondary side is now 2, and so the primary side is still 1. Okay? So again, cross multiply. I've got 1x is equal to 2. What did I just do wrong? What did I just do wrong? Voltage on the secondary side.
Straight across.
Oh, yeah. What I did was this. Okay, so, so like that. Math is hard. 2x is equal to 1. Still, what did I do wrong?
I think you had it right the first
I
time.
think I might have had it right the first
Primary
time.
side would have less than the
Yeah.
secondary.
1x is equal to 2. Oh, yeah. Yeah, I had it right the first time. 2. Shut up! So I've got 1x is equal to 2. So what do I do now? Divide both sides by 1. Okay, so if I divide 2 by 1, x equals 2. It's a direct relationship. You double the number of turns on the secondary side, then you double the voltage. Okay? All right, so what then theoretically would happen if it's a direct relationship, and this is transformer suggestion? Law, right? Which means that it happens how often? Every single time, right? So what if I changed then my number of turns on the secondary side to 1,000? What would I have down here? 1,000. If I made it 10,000, what would I have down here? 10,000. So the change in voltage is directly proportional to the turns ratio. So if I have 2 and I have 1,000, then it's still going to be a direct relationship, right? 1,000 divided by 2 is going to give me 500, right? So it's going to increase every single time. Our voltage is going to increase according to the turns ratio between the primary and secondary side. So if you're working this and your voltage goes down as if you have more turns on the secondary side than you have on the primary side, and your voltage goes down, you did what I tried to correct and got wrong the second time, right? It's always going to go up, and it's always going to go up by the difference or the ratio between the primary and secondary side. Always going to go up by the ratio. So voltage goes that way. But notice the other one. I'm going to put this as, I'll leave it intensity. Notice what happens to amperage. Amperage is intensity. What happens to amperage? Is it a direct relationship?
Inverse.
It's inverse, right? So it's inverse. So what's going to happen with your intensity or your amperage as your turns ratio changes? It's going to go down by how much? According to the turns ratio between the primary and secondary side. So if more turns on the primary side than what you have on the secondary side, then your amperage goes down. If you have more turns on the secondary side than you have on the primary side, than you have on the primary side, you have more turns on the primary. I just said that same thing again. If you have more turns on the primary side than you have on the secondary side, then your amperage decreases. If you have more turns on the primary side than you have on the secondary side, then your amperage increases, right? So it's an inverse relationship. It goes in exactly the opposite direction of voltage, but by the same magnitude, okay? So, auto transformer. What do we do with the auto transformer? It's a rheostat, meaning we can turn something up, turn something down. What else is it? What are we actually doing by sliding these contacts on the secondary side in and out? Something we're adjusting, something very specific. Not really a current. The current's going to come from that lower circuit. What are we adjusting? If we're not adjusting current, what's the other thing we adjust? Voltage. We're going to be adjusting the voltage, right? So we adjust the voltage here. And so what we call this, we're going to add another name to it. It's a rheostat, it's auto transformer, it's a variable resistor, and it's also our KVP selector, okay? So when you adjust your KVP, you push the buttons on your control panel, what you're actually doing is you're adjusting the contacts on the secondary side of the auto transformer, the rheostat, the KVP selector, the variable resistor, all those things. Regardless of what you want to call it, you're adjusting where these two things come in contact on the secondary side of this. So you're increasing or you're decreasing your voltage at this point, but we still call it a KVP selector. Why do we call it a KVP selector? Well, what's the second thing it goes into?
Step-up transformer.
Bingo, step-up transformer. Right. So what do you notice different about these two?
Second side has more coils.
Secondary side has more coils. So primary side, remember, is always the side that we supply the electricity to. We create
Alternating current.
we use alternating current to create a changing magnetic field so that we can induce a alternating current in the secondary side of the
Step-up.
step-up transformer. Right. So we select our KVP here. We call this KVP selector. We're actually going to meter the KVP over here. But where do we get our KVP? Step-up transformer. Right. So turns ratio over here varies. That's why it's a variable resistor. That's why it's, you know, all those other things. We can select our KVP. We can increase it or decrease it. This never changes. We change the contacts, we change the turns ratio here, but this one never changes. So let's say that we supply, 100 volts to the primary side of the step-up transformer. And the turns ratio is 1 to 1,000. What's going to come out on that side? Well, what's your turns ratio? It's 100 volts. There's, for every 1 over here, we've got 1,000 over there. What's our turns ratio? Okay, this is transformer law, and you can work it, but you don't have to. You really don't have to for this first test. You don't have to work it. Your turns ratio for the step-up transformer is always going to be like 1,000 to 1 or something like that. But you got 1 volt. Or I'm sorry, you got 1 turn to 1,000 turns. What's the magnitude of the increase because of that? I know some of y'all are grinning like, I got this, but you're just too shy to say it. What is it?
100,000.
Bingo, it's 100,000. It's 100,000. We had 1 turn, we got 1,000 turns. Our voltage is gonna go up by 1,000 times. We had 100 volts. We multiply 100 volts by 1,000 because the turns ratio was 1 to 1,000, right? Now we can shoot a chest X-ray. Voltage, kilovoltage selector, that's where we create it over here because we use alternating current to create a changing magnetic field so that we can increase or decrease our voltage, feed our step-up transformer whatever voltage we have selected. Now we're going to create kilovoltage so that we can go into the X-ray tube with very high voltage once we hit exposure and create X-rays, right? This portion of the circuit is not activated until you press the exposure portion of the, if it's a 2-position button, or if you're using the 2 buttons, you push prep, you get all this, and you get all this lower circuit that we're going to talk about here in a second. But this isn't doing anything yet. Okay? One other thing I got to add over there here in a minute. So off of this is our filament circuit. And with a filament circuit, we've got an MA selector, and it is also a rheostat. Why we don't draw, that one like this one, I have no idea. But it's going to be set to specific levels. Where KVP, we can adjust KVP by 1 KVP. With the MA selector, maybe that's why we draw it like that, it has specific levels. It's preset to like 100, 200, maybe 300, 400, 500, and so on. Okay, so it's specific. And then, though, what we want is we don't want our electrons to go from cathode to anode too early. Right? So what is it that makes that spark jump whenever you scoop up electrons off of the carpet? Electrostatic force. You picked them up by friction, but it's electrostatic force, right? Electrostatic force kind of sounds like electromotive force. What is electromotive force? Voltage. It's voltage, right? So if our voltage gets too high, then before we get our space charge created, electrons might jump across the tube. We don't want high voltage until we're ready for high voltage, right? So in this circuit down here, in our amperage circuit, what we're going to have is the opposite of this. We're going to feed this thing, and realistically, that 100 volts is not realistic. At this point, we're probably getting like 440 volts going into our X-ray machine, anywhere from 120 to 440 volts. But anyway, if it's 440 volts, that's too high. Electrons will jump across that gap, so we got to reduce it. So what we're going to do is we're going to use the exact opposite of this, and we're going to go with more turns on the primary side than what we have on the secondary side. And in that case, our voltage decreases. It decreases. So it goes in. When you hit your prep button, this is what the main thing that you're energizing is this. So you're energizing that so that you get a collection of electrons around that. We call that a electron cloud. Is thermonic emissions. We get hot ions, right? So we get an electron charge there. We're getting ready to make X-rays, not making X-rays yet. You're only energizing that portion, but there's another thing that you're doing. What do we say when you hit that prep button? We don't say, electron cloud up, right? We say rotor up. So then what happens also is that we energize this, okay? This is the motor that turns your rotor, all right? So I'm gonna put this down for a second. I'll show you a different one. This is what we call an induction motor. And this one, I'm not going to pass around. I'll pass around the other one here in a second. But this one's a little bit easier to identify. Each one of these things is a electromagnet. Okay, this actually came off of a washing machine. I used to have a washing machine that used this to turn the tub, and it was awesome. If you've ever moved a washing machine, they're not fun to move because they weigh a ton. But this had a plastic tub, and this was the heaviest part of it. And it's not all that heavy. One person could pick this thing up and walk around with it. It was great, but it eventually broke. But this is like a induction motor. So each one of these acts as an individual electromagnet. So what happens with this, the induction motor, is when you rotor, this is as if you're looking down onto the backside of the X-ray tube. So the X-ray tube, the glass or metal envelope is here. That thing goes around it. And it has individual electromagnets. I can't draw a square to save my life, but it's got individual electromagnets. So when you rotor up, there's a piece of, there's ferromagnetic material inside of the stem. Well, we'll go with the stem here. This is the glass. This is the stem. So if we've got ferromagnetic material in there and I energize that electromagnet, where is that going to go?
As close as it can get to that one.
It's going to move to here, so it'll get rotation, right? And if it gets to that point and I turn that one off and I turn this one on, what's going to happen?
It's going to go that way again.
It's going to go that way, exactly. And then I turn this one on, it continues to rotate. So using electromagnetic induction, what I can do is I can take that rotor and go from 0 to 3,000 RPMs in the time that you rotor up, which takes about a second. Your exposure inhibited until it gets up to speed. Why? Well, what's the main thing that kills your X-ray tube? Heat. What are these? That the whole thing is called thermonic emissions. Right, so what does that mean? Thermonic emissions. Hot. Right. So if we don't get that thing spinning, what are the three ways we deal with heat? We deal with it through convection, conduction, right? So if I put all those electrons in one spot, right, I don't spin my anode, I put all those electrons in one spot, what's going to happen to that one spot? It's going to burn it up, right? But if I spin it around and around, then where am I putting those electrons? In the same spot? Distribute them all over the face of the anode, or really the face of the target, and then we conduct it across the face of the anode. Reduce the heat load on the tube. Okay? What does this work off of? Same thing that this works off of, same thing that this works off of, which is electromagnetic induction. Right, electromagnetic induction. What's our time? I feel like I'm running longer than what I'm intended to. I'm at 50 minutes. I'm good. What time's live start?
Whatever time you finish.
I like that answer. They can wait. You don't know how mean they can be. They scare me. Everybody thinks I'm the mean one. All right, so everybody kind of sort of good with all this? You're gonna have to look this over, and you're gonna have to kind of dissect it a little bit. You know, this does not need to be your only exposure to this. You got to look at this a couple of times. I'm not saying you got to go, you know, rewatch this home. You got to read the book. You know, look up anything on YouTube, whatever. All right, so then I'm going to get rid of this, and I'm going to talk about how it is, and I've started on this, how it is that we can make our transformers more efficient, because we have loss in transformers. I'll talk about some of that. You know, you have loss in, you know, the friction in the wire. You have loss in the changing of the direction of the magnetic field. You know, anybody play basketball as a kid? Okay, running the lines. You remember that, right? So when you run the lines in basketball, what you do is you stand on the baseline, you run out and you touch the first, you know, the first line, and then you run back and you touch the baseline, and then you run to the next furthest line, and then you run back and you touch the baseline. You do that all over until you go from baseline to baseline, right? So in order to touch that baseline, what do you got to do? You can just run as fast as you can, touch the baseline, and run back, right? You got to slow down. So going back and forth, you know, just applying that to the electrons, going back and forth, do you think that there might be a little bit of I don't know, loss in that stretching and contracting of the electrons? The answer is yes. Yeah, so you got some loss there. You got some loss in heat. You got some loss in the friction, which is the heat. You've got some loss in the eddy currents, and you got that loss, and we're going to call that hysteresis. The changing magnetic fields changes, or the changing of the current changes magnetic fields. Also, the magnetic field resists the flow of the electrons. And what I mean by that is, the way I drew this before, I said, you know, north chases the direction of the electrons, right? So it's an opposition is what that is. It's trying to push, you know, the magnetic field is trying to push the electrons back out. It's unsuccessful, but it tries, okay? So that's natural resistance to those changing magnetic fields. So we have loss. Even with that loss, it's extremely efficient. So how do we minimize that? Well, you can't really do anything about the hysteresis, you know, the changing magnetic fields. It's just going to happen. We can do something about the heat we build up, all right? So the heat, we can only do certain things, but if we keep our transformer in a pool of oil, then it removes some of the heat, just like what it did in the X-ray tube. It removes some of the heat, gives the heat a place to go. Okay, so we try to keep it cool the best we can. We don't do with it what we do with superconductors, but we do still try to remove some of that heat. So we put it inside of this oil bath. And the other thing is that if we have in the, I should have been using this one all the time, if we are just using one coil of wire, that's our rheostat, our auto transformer, KVP selector, and we put a coil of wire in it, or I'm sorry, we put an iron core in it, then what happens to that eddy current? Yeah, the eddy currents reduce, right? So they reduce their intensity because they join up with the rest of the magnetic field, or a lot of them do. Maybe not all of them, but a lot of them do, right? So that we get a more efficient flow of magnetism throughout this thing. We're still gonna have a little bit of loss, but not quite as bad. Just memorize this. I honestly don't know how it works, but anyway, they use what they call a laminated core in order to accomplish this. This is not. I'm gonna go ahead and pass this around so that you can see it. The reason I use the washing machine, again, is because this is a little bit hard to wrap your mind around. But you can see in this induction motor where the coils of wire go through this core, okay? So you can kind of get a look at that if you care to. So now I've made this more efficient. So I've made a more efficient magnetism. Now let's imagine this is not the rheostat. Let me bring it down one more so I can send my wires out that way. Let's imagine that this is the primary side of the step-up transformer. So secondary side is going to be over here with a whole lot of coils. All right. So if I make a more efficient magnetism, then what am I going to induce over here? More or less voltage? More, right? So, but am I going to have the same problem over here as what I had over here with, loss of some sort? The answer is yeah. We're not really interested in the magnetism over here, but probably the magnetism is going to influence the electricity, and I'm still going to have more loss. So what if I put what if I put an iron core in that? Would that help? Yeah. So this is what we refer to as an open core transformer. It's open because it's open, right? There's nothing there. There's nothing connecting them. And one of the few things in X-ray that actually makes sense. It's open core because there's nothing connecting them. All right? So our magnetism is coming out and it's reaching in there, right? But it's also reaching out there and it's going, all over the place. It's just a mess. Right? Could I give the magnetism an easier way to conduct straight up through the center of that secondary side?
Attach it.
Well, patch it, very good.
Attach it.
Patch it, oh, I thought you said patch it, attach it, right. So if I have an open core, and I join them together, I attach them, then what do you suppose we're going to call that? Not open, but closed, exactly. It's a closed core transformer. Purpose for the closed core transformer is to take some of these and jam them straight up there. Okay, makes it more efficient. Okay, still not all that efficient because where are these going? You're still losing that, right? So what if then I were to take, everybody know what a cinder block is? Okay, if you don't know what a cinder block is, you do, but you just don't know the name of it. It's that big cement brick that has the two big holes in it, right? So what if I were to take coil number one, let's go this way, actually, not completely destroy my orange one. I take my primary side and I stick it right there. And I take my secondary side and I go right over the top of it.
Like they're intertwined.
Like they're on top of each other.
Yeah.
So where is my primary side magnetic field going?
Back.
It's going out and back in from all different directions. Does that make sense?
Mm-hmm.
So, and that's what we refer to as a closed shell transformer. Closed shell transformer is most efficient because it takes these and also, you know, make sure that there's an avenue for those to go directly up through the middle of the secondary side. Primary, secondary side are stacked on top of each other,
What's
so
the
that
difference?
everything, you know, they just all go together. Most efficient, better efficient, open core, you know, no iron core, then we've got a,
So.
there you go, solenoid, there you go. Okay? And I think that's it. I don't think I missed anything. I didn't have my notes, but I don't think I missed anything. Any questions? Some of the questions, all the questions. All the questions. Okay. So what's the relationship between voltage and turns ratio? Direct. And it goes up by how much? However much the difference is between the primary and secondary side. Right? So if I have more turns on the primary side than I have on the secondary side, I have a step up transformer. I have more turns on the secondary, primary side than the secondary side, than I have a step down. What's the what's the let's see, what's the relationship between amperage and turns ratio? Inverse. So if I have more turns on the I have more turns on the secondary side than I have on the primary side, then my amperage goes. More turns on the secondary side than on the primary. Yeah. If I have more turns on the primary side than the secondary side, then my amperage will go up. Right. By how much? What's the relationship? Yeah, difference in the number of turns. So if I have 500 turns on the secondary side, 1 on the primary side, it goes up by a factor of 500. That's voltage. If I have 100 turns on the primary side and 300 turns on the secondary side, how much does my voltage go up? It's the difference between 100 and 300. Factor of 3. Right. So it's really not that complicated. Later, you know, you'll have to work the turns ratio or the transformer laws. Primarily, I want you to be familiar with it. You should not have to put a pencil to, you know, and there will be questions about, you know, turns ratio and voltage and amperage. You shouldn't have to, you know, work them out. You shouldn't have to work them out. You can if you want to. Shouldn't have to work them out. Also, there are some questions out of DeAngelis on this. So, you know, if there are any you feel like you have to work out, you didn't do your DeAngelis, is what it amounts to. Okay? All right, test on Wednesday. Have a good weekend.